In this session, we focus on use of partial fractions in integration. If you come across an integral which is of the form, that is, the integrand is a rational function, f of x over g of x, a rational function made up of polynomials, both at the numerator and the denominator, then you are likely going to use partial fractions, but you have to be very careful. There are integrals of this form that can be done simply by recognition. If I have the integral in such a way that h prime of x all over h of x dx, that means the rational function is in such a way that the numerator is either an exact differential of the denominator or it is a constant multiple of the denominator. When that happens, recognition tells us to just have the integral as ln of the denominator plus the constant of integration. You have, for instance, integral of 1 plus 2x all over x squared plus x minus 6 dx. Usually in these type of cases where the denominator of the rational function is a polynomial that can be factorized, you begin to suspect partial fractions. It's either you have a factorizable quadratic or difference of two squares. But in this case, you would have to always verify whether recognition can't go, whether you can't use this fact that the numerator would be an exact differential of the denominator or a constant multiple of it. Like this case now, we can see that if we differentiate the denominator, we have 2x plus 1, and that 2x plus 1 is found at the numerator. So this integral would simply be ln of the denominator, which is x squared plus x minus 6, plus the constant of integration. If we instead had integral of 2x plus 3 all over x squared plus x minus 6 dx, you can see that the differential of the denominator is no more the numerator, like in the first case. In this case now, the recognition fails and we are bound to use partial fractions due to the fact that the denominator is factorizable. So I could rewrite this integral as 2x plus 3 all over x plus 3 into x minus 2, as these are the factors of the quadratic. And at that point now, I would have to integrate a over x plus 3, some constant a, plus b all over x minus 2, which is now easier to integrate. In particular, where there are linear factors at the denominators as you do your partial fraction, you would have to use this integral of 1 all over ax plus b, a linear factor at the denominator. This would be 1 over a ln of ax plus b. So it's a standard integral that you need to master. It has actually resulted from this recognition formula here. If I differentiate the denominator, I have a. But at the numerator there, I don't have a. So it's like putting a there and then 1 over a so that the numerator becomes an exact differential. You now get this result. So if at some point I have done my partial fraction and I get 3 all over x plus 1 plus 4 all over x minus 2 to integrate, my result would then be, I will write 3 as is the constant, then ln of the denominator x plus 1 plus 4 again, which is the constant, ln of the denominator, which is x minus 2. plus c. If I had instead 4 all over 2x plus 1 minus 5 all over 3x plus 1 all dx, after doing the partial fraction, my result would be 4 divided by the coefficient of x at the denominator, that means the differential of the denominator, which gives 2, then ln of the denominator, minus 5 again divided by the differential of the denominator, which is 3, then ln of the denominator, which is 3x plus 1, plus the constant of integration. So these are cases where linear factors are involved at the denominator. In the case where you have repeated factors at the denominator, this integral would be used. It gives ax plus b to the power n plus 1 all over n plus 1 into the differential of the bracket, which is a. So if after doing my partial fraction I get something like 1 all over x plus 1 plus integral of 3 all over x minus 2 all squared at some point, then I will have, this one is a linear factor at the denominator, so just 1 over the coefficient of x, or the differential at the denominator, which is 1, so I just take ln of x plus 1, plus I will have to rewrite this as 3 integral of x minus 2 to the negative 2 dx. This will now give ln of x plus 1 plus 3. I now apply this formula, x minus 2 to the power negative 2 plus 1 all over the result of that power, which is negative 1, into the differential of the bracket, which is 1, plus c, and that gives ln of x plus 1 plus, or rather minus 3 all over x minus 2. The result of that power, x minus 2, will be negative 1. So it leads to x minus 2 to the negative 1 being 1 all over x minus 2, which gives this. Now, in the case where you have, so this is the case for repeated factors. In the case where there are quadratic factors at the denominator, you would need to use this standard integral, which equals 1 over a tan inverse of x over a plus c. And if I need to integrate, for instance, 1 all over 1 plus x squared dx, I would simply have tan inverse of x plus c. If I have integral of 1 all over 3 plus x squared dx, the standard integral says I put 1 all over the root of this constant, then tan inverse of x all over the root of that constant plus c. If I instead have 1 all over 1 plus 5x squared dx, I would need to begin by factorizing the 5. So I'll have integral of 1 all over 5 into 1 all over 5 plus x squared. and that gives 1 over 5 dot 1 all over the root of the constant, which is 1 over 5, then tan inverse of x all over the root of 1 over 5. Overall, I will get root of 5 over 5 tan inverse of root 5x plus c. If after doing my partial fraction, then I come up with this integral to do 1 all over 3 plus x plus 2x plus 1 all over x squared plus 1, like it would normally happen most of the time, I will recopy and distribute the denominator. So I will recopy and put 2x over the denominator plus 1 over the denominator. That makes it easier to integrate. So I'll put 2x over x squared plus 1 plus 1 all over x squared plus 1. All that dx. So where there is a quadratic factor at the denominator, there will be a linear factor. The numerator has to be linear. So when you come out with the numerator, with that linear numerator, you distribute that quadratic factor that is at the denominator. It will now be easy to integrate. In this first one, I simply have a linear factor at the denominator. So the integral is ln of the denominator plus the integral of this part here is by recognition. You can notice that the differential of the denominator gives the numerator. So ln of the denominator becomes the integral plus this other one is tan inverse. So the integral of 1 all over x squared plus 1 is simply tan inverse of x plus c, and that gives the integral. So take note of these cases where there is a quadratic factor at the denominator. The other cases involve where you have improper fractions. You could have this case, which is common, x plus 1 all over x minus 1 dx. And here we need to use long division, but there is a way of doing it without going through long division. In this method, we copy the numerator, start by copying x and putting plus 1 far ahead, leaving some space, and that space will be filled by the constant at the denominator, which is -1, and neutralized with 1. So the aim is to make sure the factor that is at the denominator appears at the numerator. That factor will be maintained, then I simplify what is there and then distribute the denominator. So I will get x minus 1 over x minus 1, which is 1, and then 1 plus 1 is positive 2 all over the denominator also. It gives you the partial fraction directly. And so the integral now would just be x plus 2 ln of x minus 1 plus c. If it were x squared plus 3 all over x squared minus 1, I would have to use that method again. First, to do the long division, I will write x squared plus 3, and down I have -1. I will put -1 plus 1, neutralize it so that it gives back what was at the numerator, all over x squared minus 1. From there now, I group the term that is down, will be maintained, then I simplify what is on that side. So I get this over this, which is 1 plus 4 all over x minus x squared minus 1, sorry. So I will now have to integrate this, but again, you see that this term still needs to be broken down into partial fractions as the denominator is factorizable. So that gives 1 plus a all over x plus 1 plus b all over x minus 1. And that is how you're going to find your values of a and b and then do the integral to complete.